Welcome to lesson 2.3, Converses. So we've already looked at the idea of conditional statements being if-then statements with a hypothesis and conclusion, or an antecedent and consequent. And today we are going to build off that idea and look at converse statements or converses. So in the first case, though, we are just going to look at our big idea, which is that every conditional statement has a converse. So no matter what, every conditional statement has a converse. So here is a true conditional statement. If you own a Chihuahua, then you own a dog. So then that can be represented in a more algebraic or mathematical model. And in that case, we could represent you own a Chihuahua, the antecedent, with the letter C. And then the letter D can represent our consequent, you own a dog. So then the conditional statement can be written in the symbols, and this would read, again, if C, then D. So the double arrow tells us it's an if-then statement. So what's on the left is the if, what's on the right is the then. So this conditional statement would be true because every Chihuahua is a type of dog. Now, if we reverse that conditional statement to be if D, then C, so that would read in words, if you own a dog, then you own a Chihuahua, is it still true? And if not, provide a counterexample. So let's look at that statement again. When we reverse it, our original conditional reversed becomes if you own a dog, then you own a Chihuahua. Well, that's not necessarily always true, because you could own another breed of dog, my example, a bull mastiff, my breed of dog, but there's thousands of different breeds of dogs that you could own that is not a Chihuahua. So that would be an example of a converse statement. When we reverse the antecedent and the consequent, we create a converse to the original conditional. So anytime we have a conditional, if we reverse that hypothesis and conclusion, or the antecedent and the consequent, then we have created a converse. So we're just switching the order. So it goes from if C then D to if D then C. This would be the converse of the original conditional here. So example 1 asks us to write the converse of the statement and then state if the statement is true and if the converse is true. So our original conditional statement is if you live in Kentucky, then you live in the United States. So the converse of that would be if you live in the United States, then you live in Kentucky. So is the original statement true? Yes, because in order to live in the state of Kentucky, you also live within the country of the United States. Then if I look at our converse, the converse, if you live in the United States, then you live in Kentucky, is not necessarily always true. So we would call that a false statement because there's 49 other states that you could live in. In part B, it says if x equals 4, then x plus 2 equals 6. So that's our original conditional. So our converse would be if x plus 2 equals 6, then x equals 4. So in our original conditional, that would be true because no matter what, 4 plus 2 is 6. And then our converse, if x plus 2 equals 6, if we would solve for x, the only solution we would get is x equals 4, so that is also true. Then example 2 is looking at a Venn diagram again. So the Venn diagram at the right shows the relationship between the figures that make... that did not print well. I apologize. So I printed really weird. So we'll look at this a little different. It's supposed to read the S on this line, and part of this got cut off. So rewording this slightly. So our Venn diagram here, we'll just say, shows the relationship between squares and rectangles. And in this case, when we want to write this out, S will equal a figure is a square, and R will equal a figure is a rectangle. And this part should have been up here. So this original statement should read, the Venn diagram at the right shows a relationship between the figures that make it true. So A reads, write if S then R in words. And remember, S represents a figure as a square, and R represents a figure as a rectangle. So write if S then R in words. So if it is a square, then it is a rectangle. And is that true according to the Venn diagram? Well, all of our squares are contained within the rectangle circle. So all squares are a special type of rectangle. So this is a true statement. So part B asks us to write the converse in words to this conditional statement from part A. So writing that converse in words, we're reversing the antecedent and the consequent. So it would become, if it is a rectangle, then it is a square. And then if we look at that, we know that statement is not always true. So we would need to provide a counterexample if we're going to state it as false. So we know there's rectangles that exist that are not squares. So we could provide any example. A 3x7 rectangle here would be one example. Then we move into example 3. And they're saying let P be the statement, the absolute value of x is less than 5. And let Q be the statement, the absolute value of x is less than or equal to 4. So in this case, they want us to begin with drawing a graph of each inequality on a separate number line. So a refresher from Algebra 1, if we are going to graph inequalities, if it's just less than or greater than, we know we'll be using open circles. And we want to consider what numbers could take the place of x to make this statement true. So the absolute value of 5 is equal to 5, and the absolute value of negative 5 is equal to 5. So we know we would have our open circles at 5 and negative 5, and the absolute value would be anything in between that could work for x. So representing this absolute value of x is less than 5 on a number line would be open circles at negative 5 and positive 5, and our line connecting them showing all values in between, but not including 5 and negative 5. And then to graph on a number line, the absolute value of x is less than or equal to 4. Because it's an or equal to, we will use filled in circles. And the values that equal this would be a 4 and -4. So any values in between and including -4 and 4. In part B, they want us to write if P then Q in words. So P was if the absolute value of X is less than 5, then Q, the absolute value of X, is less than or equal to 4. So is this statement true? Explain your reasoning. So is it true that if the absolute value of 5 or X is less than 5, then that absolute value of X is also less than or equal to 4? There's a couple ways we could think about this, but the fact that we already graphed these on a number line, if we would take this graph here and place it over this graph here, are there numbers that exist outside of this second graph that we put on top of the first? Yes, there are. A -4.9 is less than 5 for its absolute value, but its absolute value is not less than or equal to 4. Same with 4.2 or 4.81. So there's many values that are less than 5, but their absolute values are not less than or equal to 4. The converse to that statement would read, if the absolute value of X is less than or equal to 4, then the absolute value of X is less than 5. So is this converse true? Explain why or provide a counterexample. So yes, this would be true, because if the absolute value of X is less than 4, then the absolute value of X is less than 5. We could look at the graphs yet again. In this case, we're saying if we have this graph here, does that include all the values needed from this graph also? So if we're looking at the absolute value of X being less than or equal to -4, would this fit completely inside of this? And yes, it would. So in that case, all the values are contained. So all the values for the absolute value of X being less than or equal to 4 also lie inside the graph for X, or the absolute value of X being less than 5. And then moving on to our final example here, example 4. Example 4 asks us to consider the statement, if n equals 3, then n squared minus 5n plus 6 equals 0. So in this case, our if-then statement is an algebraic equation and a substitution. So we can simply solve by plugging or substituting the 3 in for n in both pieces of this equation. So if we do that, we end up with 3 squared minus 5 times 3 plus 6 equals 0. 3 squared is 9, minus 5 times 3 is 15, plus 6. 9 minus 15 is a -6, plus 6. 0 equals 0. So yes, that would be a true conditional statement. The converse would read, if n squared minus 5n plus 6 equals 0, then n would equal 3. So in this case, to check if that converse was true, we would in fact be able to factor out the trinomial to find if it has more than one solution. So again, going back to algebra skills and looking at the idea of factoring. So in this case, we have a trinomial, 3 terms. So we're going to take our n squared minus 5n plus 6 equals 0 and factor it into our two binomials. So we're looking for two values that multiply to be 6 and add to be negative 5. So in that case, a negative 3 and a negative 2. So n minus 3 and n minus 2 are our two binomials. In that case, n minus 3 equals 0, and n minus 2 equals 0. So n could equal 3, or n could equal 2 to satisfy this equation. So is our converse true? No, because we have more than one possible answer. So our only possible answer is not 3. N could also equal 2. So, as you work through today's practice problems, the key ideas from today are obviously the fact that we have our original conditional if-then statements. We have our way to represent that with symbols, reading if C, then D. And then we have the converse, which is when we reverse or exchange the antecedent and the consequent. So if our original is if C, then D, our converse would read if D, then C.